Welcome to the Deep Dive, where we challenge our assumptions about how things work. Today, we're plunging into an intriguing invention that doesn't just tweak aircraft design, it completely reimagines it. Our mission for you is to unpack a concept called parallel aircraft wings. Imagine a wing not sticking out to the sides, but running along the fuselage. That genuinely flips the traditional image of an aircraft on its head.
It really does. And what's truly captivating here is how this invention seeks to overcome fundamental challenges in aircraft design, drag, stability, landing efficiency, by fundamentally rethinking the most iconic part of an airplane, its wing. It's about achieving more lift, maybe enhanced safety, and some unique capabilities through an entirely different configuration.
Okay, let's unpack this then.
Yeah.
The fundamental idea behind these parallel aircraft wings, as you said, is arranging them along the length of the aircraft. The inventor states this configuration aims for less wind resistance and more lift. How does that even work, especially when, traditional wings stick out so wide? What's the core principle being challenged here?
Precisely. Yeah, the typical approach, it really focuses on wingspan and aspect ratio. What's truly insightful here, or at least the inventor's hypothesis, is this. They posit that for air pressure to efficiently close behind a wing at high speeds, so minimizing turbulent drag and maximizing lift, it needs more length or maybe time along the airflow.
Okay, length or time?
Right. Traditional shorter wings, they argue, might generate significant aerodynamic losses because the air doesn't have that kind of extended path to recover smoothly. So this design fundamentally redefines the relationship between wing geometry and pressure recovery. It's quite a fresh perspective in aerodynamics.
That's a fascinating theory, linking length to pressure recovery.
Yeah.
But practically speaking, traditional wings get so much lift from their camber and angle of attack. How does this parallel design generate enough lift for takeoff, especially at lower speeds, if its main advantage is this time to close thing at high speeds?
That's an excellent question. And it's something the invention implicitly addresses through its movable struts. It suggests the primary wings can actively adjust their position relative to the fuselage, to achieve different aerodynamic profiles for takeoff and landing. But it does raise a critical engineering challenge, absolutely. The complexity of coordinating all those moving parts for precise control through all the different flight phases, that's significant.
Okay, so assuming they solve that complexity, if these parallel wings are theoretically more efficient, that's one major benefit. But in aviation, efficiency often goes hand in hand with another crucial factor, safety. What does the invention propose on that front?
Well, the document outlines several pretty intriguing safety advantages. First, it suggests less danger of accidents with other objects and birds, maybe just because the aircraft looks compact. It also claims this compact appearance brings more harmony to the aircraft's aesthetic, which is, well, subjective but interesting. But a critical point to consider is how it's protected from crosswind loads.
Crosswinds, always a factor.
Exactly. The invention states that the control mechanism, the storer work, which is placed laterally in the middle of the wing, helps ensure the aircraft remains protected from crosswind load because it stands in the shadow of the aircraft.
In the shadow of the aircraft, that's an interesting phrase. Does that mean it's physically hidden, or is there a deeper aerodynamic meaning there?
Right. It's not literal shadow, of course. It implies the control mechanism is positioned within the relatively undisturbed airflow created by the main body of the aircraft. So essentially shielding it from direct buffeting crosswinds. It suggests a pretty clever integration of control surfaces with the core design for stability, potentially making handling in gusty conditions, smoother and more predictable.
Okay, that makes sense. So it sounds like a more compact, potentially more stable aircraft. And with that compact design, is there also potential for increased utility, maybe even in carrying capacity?
Precisely. The invention also notes that the wing surface can be enlarged for carrying capacity. This makes the concept particularly interesting for cargo planes and transporting many passengers. So it's not just about speed or safety, it's about practical utility, opening up possibilities for larger payloads or maybe higher passenger counts. That's a significant economic advantage if it can be realized.
Now here's where it gets truly unexpected for me. The invention describes a unique way this wing can brake strongly. How does that work? And there's a fascinating detail about energy recovery, too. Plus, the inventor uses this rather vivid phrase, without hip-hop. What does that mean in an aviation context?
It's a striking image, isn't it, without hip-hop? The design claims the wing can brake strongly more efficiently, specifically by pressing down on the ground. When the inventor says without hip-hop, what they likely mean is a stable, firm, perhaps even vibration-free braking action, avoiding the kind of bouncy or unstable engagement that can sometimes happen with traditional landing gear or air brakes. It really speaks to a controlled, powerful deceleration.
Okay, stable braking and the energy recovery.
Right. And to connect this to the bigger picture of efficiency, the invention states that energy can also be recovered during braking. This implies a potentially greener aspect to the design. Kinetic energy during deceleration isn't just lost as heat, but harnessed, perhaps for onboard systems or even to assist in the next takeoff.
Hmm. While the idea of simplified braking and energy recovery is appealing, anyone familiar with large aircraft will immediately think of the incredible forces involved. How does this design propose to manage those forces, especially when pressing down on the ground, without stressing the airframe or causing instability during deceleration? That seems like a major engineering challenge.
That's a critical consideration, absolutely. The document focuses primarily on the mechanism of the braking action, maybe less on the detailed structural implications, but it implicitly relies on the inherent stability and presumably the robust construction of the parallel wing system itself to absorb and distribute those forces. It's a bold vision, for sure, but like any radical shift, it would face rigorous scrutiny in terms of real-world performance and structural integrity. Proving its stability during such intense braking maneuvers would be key.
Definitely. So we've talked about the why and the what, the potential benefits, but how does this revolutionary wing actually function? Let's get into the mechanics described in the invention.
Okay, right. This is where the engineering really comes to life. The main wing is arranged on the aircraft roof. It's supported by 2 struts at the front and at least 1 strut at the back, and critically, all these parts are movable.
Movable struts. Okay.
Yes, the key is that all struts are separately movable up and down. This allows the entire wing to fully lift and brake. For achieving lift, you'd either raise the struts at the front or lower the rear struts. Makes sense.
Mm-hmm. Changing the angle of attack effectively.
Exactly. Conversely, for the braking position, you would either raise the rear strut or lower the struts at both front points, pushing it down.
That flexibility sounds like it could offer a lot of control. Does this movable design also factor into how the aircraft maneuvers in the air? Or is it primarily just for lift and braking?
No, that's a key aspect to maneuverability. The separate, independent up and down operation of the struts gives the wing the ability to pivot right and left, essentially. This allows the aircraft to maneuver in the air. So it's not just a passive structure, it's an active control surface in itself.
And there are side wings too, right, to complement this main structure.
Yes, exactly. The side wings are mounted on a rotatable axis. By rotating this central axis, the side wing can also achieve a lift or braking position. And remember that control mechanism, the store work we talked about earlier for crosswinds.
Yeah.
The inventor states it's located on the side wing and can be steered right or left. So this shows a pretty comprehensive system for control and function, where both the main and side wings play active roles in the aircraft's flight dynamics.
So you've now taken a deep dive into the fascinating concept of parallel aircraft wings, a design that really aims to redefine lift, safety, and even braking. It genuinely flips the script on conventional aircraft design.
We've explored how just shifting the wing orientation could, according to this invention anyway, lead to less wind resistance, more efficient lift, enhanced safety against crosswinds and objects, and even the ability to recover energy during braking. It's truly a different way to think about flight mechanics, and it opens up a lot of questions about how aircraft could look and operate in the future.
What stands out most to you about this design? Is it the mechanical ingenuity, the bold claims about efficiency, or maybe just the sheer audacity of proposing something so fundamentally different from what we're all used to seeing?
Well, it's all pretty striking, isn't it? But I think this begs the question for you, the listener, to consider. If such a design were actually realized, how might it fundamentally change not just the appearance, but the entire operational paradigm of future aircraft? Think about how they're built, how they're flown, even how they land. What further engineering hurdles or perhaps unexpected advantages do you think such a radical departure from traditional wing design might present?